Hi everyone. So we're talking about Keplerian telescopes today, and it is also known as astronomical telescope. Generally speaking, telescopes are used to magnify distance objects. So telescopes magnifies distance objects, unlike microscope. The microscopes magnifies uh, objects. So microscope magnify objects, while telescope magnify distance objects. And then the Keplerian telescope, just like the Galilean telescope, is actually one of the low vision devices too. It can also be used as low vision. It's just that there are some issues with it. It's quite bulky, and then the image is inverted. So if someone has low vision, you don't want something that has the image that's inverted. So that's why it's not commonly use like that, then you have to add something else to it because it's quite bulky. So now the optical diagrams, just like we said in Galilean telescope, this one it consists of two convex lens. No, Galileo has a convex and a concave lens. The Keplerian telescope has the two lenses are convex. So of course, the objective and eyepiece. Okay, the eyepiece is always bigger than the objective lens. So just like in Galilean telescope too. But in this case, they are both convex lens. Unlike Galilean is one is convex, the other one is concave. But in Keplerian, the two of them are convex lens and they are both objective lens and of course the eyepiece. And then they're separated by the sum of their focal lengths. So this effect of these two lenses that make it very, very powerful. And that's why it's very, very powerful because it's like a combination of two lenses. It's some of the focal lengths. One lens add together, they make a bigger lens. Unlike the Galilean telescope, that one lens is positive, the other one is negative. And so their effects will be different a bit. So it's not as magnifying as the Keplerian, but of course, Keplerian is so bulky. So that's the difference. So Keplerian consists of two lenses, two convex lenses, okay? And then that's separated by the sum of their focal lengths. So to draw the optical diagrams, so we put our eye, the objective lens first. And of course, the eyepiece. It's not a common thing to ask in the exam. It's usually the questions on MCQs on it. So, just understand the diagram that you can see. These are represent the convex lens. So, they are both convex lens for Keplerian telescope. And this the first lens, which is the smaller one, is the objective lens. Okay. So this first one is objective lens, and this other one is the eyepiece. So the objective lens and eyepiece. Okay, so now in Galilean, the idea was that the where the parallels of light are coming, they focus on a plane, which the F2, the second focal point, will coincide with the first focal point of the negative lens. So the second focal point of the objective lens, so the convex lens, coincide with the first focal point of the negative lens, which is the concave lens. But this is not the same with astronomical. For astronomical, the rays that are coming, they're going to form at a point that will coincide. So the parallels that are coming will coincide with with exactly the F1 of the positive lens. Now, about positive lenses, that's where the difference will come in. So the two lenses also still coincide, but just that where the parallels of light are converging to, which is the F2 of the positive lens, is about an F1 for the eyepiece, which some people will not put the F1 and F2, just put the FO and then the FE. This is what I'm trying to say. So we have the FO here, which is like the where the rays are really where they are originating from. So you can have multiple rays to view this for the galenium. So you can have ray coming, all of them are parallel. I have one that pass to the center too. They have to be parallel to each other. So you have to be very careful by drawing that. You can see these two rays are parallel. And then you could also have a third one if you want. If you want, you can have a third one. And making sure it's as parallel as possible. And so put arrows. So nowhere parallels of light will converge to be like the F2. Okay, so but let's call that F0. You know, we define F2 from spectral lenses as point of convergence or divergence of rays. In this lens, in this case, is a positive lens. It's going to converge to, so it's going to converge to BT F0 here. So it will converge those rays that are coming from infinity will converge to here. So the one that's coming that pass to the center of the lens, of course, will go in the vertex. So it's always good to draw that one first. And then you can now converge these other ones to it. So you converge to because the convex lens, and then they're going to converge at FO because it's the point of convergence. So the FO is like the F2 for the convex lens now to get that the F2 for the convex lens. So the image is going to be here. That's the first intermediate image. Let's see. So that is where, and that's now the beauty of it, just like we said in Kalina too. So that where the image from will now coincide, which is from at the F2, will now coincide at also coincide with the FE for the eyepiece. So the IE is eyepiece, the O is objective lens. So the FO here, we are saying that is the focal length of the objective lens. That's the name of the FO. While the FE is the focal length of the eyepiece. Let me just put that as a tag here. FO equals to focal length or focal point, which focal point is much better of objective length. While the FE is equal to focal length, focal point of eyepiece. So now once it has formed, so it is now formed at, so you can see the FO and FA will not coincide, so that's the coinciding. But of course, now since it's now located at F, I know it's already located at F, now if you want to continue to meet this other lens, the second lens, you bring a, from the bottom of the image now, parallel to the principal axis, okay? The other also from the bottom, parallel to the principal axis is going to pass through, at least like to being created pass to the center first because it will determine what will happen to the other rays. I know once the object, this will not be as a new object. The first image is formed by this lens, which is as an object for this other lens. I know once the object is at the F, the emerging rays are parallel. Again, these are talked about in lenses. They get so these are lenses. Who's how to draw their diagrams. So once the object is located in the FE, the emerging rays, once it gets to the lens that you want to act on, the emerging rays need to be parallel. So the emerging rays, the two rays will not be parallel to each other. You can see these two emerging rays are parallel to each other. And so like the unlike in Galilean, that the emerging rays are uh, they're equally stable actually, but there's a way they appear that is a little bit different from the Keplerian. So these ones are also parallel to each other, but you can see. So it's when you now extrapolate there is you know that it's actually going to be form at infinity. So you could extrapolate a bit like this. So and that's the Keplerian telescope. Again, they are both convex lens, okay? And the they're separated by the sum of the focal lengths, the two effects of the focal lengths that give us the Keplerian telescope. And you can see the parallels that are coming from infinity. You first converge at the FO, which will coincide with the F E. And so from there, the new image that's formed is going to become parallel. And so that is what happened. As you can see the angle here that is formed there, you can see that it's a little bit bigger in this place. So that's just what the Keplerian telescope does. It's helping magnify things, so just like a Galilean telescope, or just that image formed by Keplerian, the image formed by Keplerian, the image is inverted, and so that is the issue with it. If the image is inverted, that means you cannot. So that's a low vision. You have to put something in it, and so pro prism sometimes is used to make it. And so that means the cement is going to be very big. So that's why the cement is usually compacted. It's usually bigger than the Galilean telescope. So the cement usually keep bigger than the Galilean telescope. And also, don't forget about the magnification. You know, we say magnifications generally for telescope is equal to minus FE over FO. Now, for this, since the FE is a positive length, so it's just minus plus. I put plus anyway, so eventually over FO, the magnification will be negative. So which should suggest an inverted image. Okay, so image. So that's the magnification is negative there. So unlike in Galilean, one is negative, the other one positive. By the time you drive that one, it's going to be positive magnification. So it suggests a negative image. So that's the Keplerian telescope diagram. Um, so let me just show you a couple of just my difference in the two again. They both have magnification, but the Keplerian magnification is usually very much, as I've said, because it takes some of the focal length, unlike Galilean, which is the difference in the focal length. So Galilean will not magnify as much as Keplerian. If you want something very, very magnification for a very low vision, you can use Keplerian, but you have to put something in it because the image is inverted, as I've said. So you have to incorporate polar prism images. So it's going to be bigger for them. Of course, Keplerian is large, more field of view. The field of view is large and sharp compared to Galilean that are small. And so, and the size, of course, Keplerian is bigger than the Galilean telescope. So that's that for the Keplerian telescope.